Data Skeptic is the official podcast of dataskeptic.com, bringing you stories, interviews, and mini episodes on topics in data science, machine learning, statistics, and artificial intelligence.
Okay, Linda, today we're going to talk about something called Big O analysis. Now, you probably have no background in Big O, correct?
I feel like you mentioned it.
Yeah, I guess maybe it comes up from time to time, but let's actually get into what it means today. So Big O is a type of analysis that computer scientists predominantly do that studies the runtime of different algorithms. So let's start with a simple example. How do you calculate a restaurant tip?
Well, if you're Kyle, you just do 20%.
Yeah, it's easy, right?
If you're Linda, me, I only do 15 unless they're above and beyond, then it's 20.
Well, but how do you actually get the number? So you have the total. How do you get to the amount you want to write for the tip?
You calculate 20%.
I do. You calculate 15. So how do you do it? Well, how do you execute the multiplication?
If your bill says X amount, I move the decimal point 1 to the left.
That's like 10%.
That's 10%, and I can multiply by 2. That's 20. If I don't want 20, I take half of that and add it back on.
Okay, so that is an algorithm. First you multiply by 0.1, and then you add a half.
Sure.
So 2 steps. Now, does it change relative to the size of the bill?
Yeah, that's why I said you take the bill size.
But I mean, does your algorithm change? Do you calculate it differently if it's a...
Oh, I thought you meant did the tip change?
No, the tip always changes, of course.
Yeah, so I meant, of course the tip changes.
Yeah, your procedure. Does your procedure ever change?
No.
Right. So the algorithm doesn't change with the input size. That's a constant time algorithm right there. Every restaurant tip, basically you follow those 2 steps and you're done.
Well, that's the definition of a percentage-based tip, too.
Yep, that's right. Now let's talk about a little bit more complicated algorithm. What if I gave you a deck of cards? Not like a one that I just got out of the store, one that came out of a drawer and we don't know where it came from, so we're not sure if it's like a correct deck or whatever. And I want to ask you the question, does this deck have 2 Queen of Hearts in it?
Well, I'd have to go through the whole deck and look at it.
Yeah, so you'd have to basically scan through the whole deck and count the number of Queen of Hearts you encounter, right?
Yep.
So you have to look at every single card.
Yep.
Now let's say I gave you a deck that looked to be about 52 cards, like a standard deck, right? And then I gave you a second deck that was about 3 times taller than that. How much longer do you think it'll take you to check if there's 2 Queen of Hearts in the larger deck?
Well, I'm going to guess 3 times as long.
That's right.
But there's a chance as I'm flipping cards, I optimize that and get faster as I go.
How would you possibly optimize this algorithm?
It's not an algorithm. I just optimize my actual physical doing of flipping the cards.
Oh, you mean like your dexterity kind of,
yeah.
Right? So you're correct, but we're going to need to leave that out of the equation. And let me make an analogy why. In the computer world, Moore's law and all, computers are getting faster. You can get better RAM, better whatever, overclock. You can do all these things to make your computer run a little bit faster. That's just going to be kind of like a constant value. Like if your computer is 10% better than mine, it should be 10% faster on all the tasks, give or take. So yes, you're correct. Dexterity can be improved to get your speed a little higher. But if we think of time in the number of steps to execute, it's just going to take 3 times longer.
Sure, that's a very simplified and linear way to look at it.
I don't know if I'd say simplified because this is the core of computational theory. It's counting the number of steps and then not exactly worrying about how long each individual step takes on a computer. And now, of course, you could make an argument here like, well, what if this computer is better at, a specialized task than another? And you can build a case for that, but there's some advanced reasons we won't get into today of why we only just care to count the number of steps. And you hit on the other key thing. The find if there's 2 Queen of Hearts in the deck takes linear time. Linear in the size of the deck. So if I triple the size, it takes you 3 times the time, right?
Sure. That's a good estimate.
What about 10 times the size?
We're going to guess 10 times the amount of time you need from the original.
Do you remember a while ago we talked about binary search, finding if a word was in the dictionary?
Oh, vaguely. Dictionary, yes. Ringing a bell.
Yeah, I had to go buy a dictionary to do that show.
You did not.
I did, remember? I got it for like $3.
Well, where is it?
It's in the garage.
Okay.
You'll recall that if you wanted to find out if a word's in a dictionary, you could also do it in linear time, right? You could check every single word and see if it matches your word, and you'll have to look at n number of words where there's n is the size of the dictionary.
Well, you don't have to check every word because
Correct.
it's in alphabetical order.
Yeah, so what do?
You just do it by the alphabet. That's not smart to check every word.
Right. We're going to use binary search where you go to the middle and you say, is my word before or after the middle word?
Right. And you keep dividing it in half.
That's right. So that divide in half procedure, if you graphed out the amount of time it would take, we call that a log of n algorithm. Because as n goes up, if I brought you a bigger and bigger dictionary, every time you take one step, you cut the size in half. So it doesn't take you linear time like finding the two queens. You can actually be really efficient and fast in looking up any size dictionary.
What can't you do with the deck of cards? Cut it in half and say, is the queen in this half or the other half?
You're thinking ahead now. That would require some parallel processing where you cut it in half and give it to two people and ask them to like count up the number of queens they encountered and then reduce that back where everyone adds their numbers together. So yes, certain algorithms can be done in parallel that way. We're not going to talk about that till later future episodes. So for now, let's just assume we're talking about one person is doing the procedure. And in that respect, find the queen is linear time, find a word in dictionary is log of n time. It's faster.
Mm-hmm.
Let's talk more about n. N is the size of the input. So in the case of the dictionary, the size is how many words are in the dictionary. In the case of the deck of cards, it's how many cards are in the deck. The whole thing to understanding big O analysis to get started is figure out what is your input and how do you measure its size. Now let me give you another one. What if we're at the grocery store and you have a shopping list?
I like to use Google Keep.
Yeah?
Turn on their checkbox function and enter my groceries into there.
Yeah, you are quite diligent about the grocery shopping.
I hate opening the cabinet and not seeing the thing I need when I'm already ready and I have time set aside to bake something.
That's why you got to get two every time.
No, that doesn't
That's
help.
easier.
I just pay attention to when things run out.
All right, we have your way and we have my way.
What's your way? You just buy two every time?
Yeah, just wing it. I don't have time to deal with this. Hope for the
So
best.
if you open it and it's not there, you just change course?
Yeah, it's like jazz. But let's do shopping your way, okay? Now, one thing you have to do at the end of the day is determine, do you have all the items in your cart that are on your list?
Well, you just look at your cart and you go down the list.
What's the n size here? What is n in this problem?
Oh, the problem is how many items are in your cart.
That's right. Or on your list, because you ultimately want to fulfill the list.
Mm-hmm.
So describe for me now the steps. What's the procedure to do this check?
Well, you could either look at your cart first or look at your list first. But you can look at one of them and then compare.
You're thinking too high level. You need to think more like a computer scientist. What are the individual steps? Imagine like I'm a complete moron. You need to walk me through this.
Well, why don't you just tell me? Since you're the computer scientist,
All right.
you should just walk us through.
Okay. You start at the top of the list. You go to the first item. And then you say, is this item in my cart? But that is not an atomic step because your cart has n number of items. So you have to look through all of the items until you find the one you're looking for. So worst case scenario, you might pick the one you're looking for last. On the first step, to confirm if you have the first item, you'd have to look at the n items in your basket. Then you go to the second thing on your shopping list and you say, is this item in the basket? And now you might possibly, worst case scenario, need to look at all the items again. So for every n item on your list, you have to do n more operations. N times n equals n squared.
But the thing is, it would be n minus 1, because assuming you found that item.
All right. Yeah, that was the exact objection I had on the first day I learned about all this stuff. You're going to have to move past that. The minus 1 is like a constant, so it doesn't, even though you're right, it's a little bit faster. We think asymptotically when we talk about these things.
What does that mean?
That means as n gets really, really big, how does the algorithm play out? Your cart, let's say you have two items, you don't really execute an algorithm. You just look, you're like, are the two items there? Yes, they match. It just happens so fast, it feels constant. But what if we were planning a big event and there were 1,000 items we needed to get? Well, now it's not so simple of saying like, how did I confirm? You actually even have to figure out if you want to have this n minus 1 advantage you're describing, you have to take extra steps to move that item somewhere else and make sure you're deduping and this kind of stuff. And even if you do all that, yes, it might be a little faster, but asymptotically, it's still going to be slow. So as the size of the shopping list grows, it grows comparable to the function n squared. So it takes like increasingly more time each step. And that little minus 1 you're talking about, that little small advantage you can get, it doesn't really show up in the grand scheme of things. It's kind of like, how much money are we going to put in savings this year? And if we put one extra penny in, like, yeah, we'll be better off at retirement, but that one penny is not going to make a world of difference.
Interesting.
So you got to get past these like little small constant time efficiencies and just think about asymptotically the big pictures.
Okay, data skeptic listeners, I bet at least a few of you are screaming at your phone right now because you know of a smarter way to solve this shopping list problem than the way I described, and you think I missed it. Come on, who do you think you're dealing with here? My example is for descriptive purposes. The algorithm I described to Linda indeed has a big O of n squared time. It takes n times n number of steps to complete. And while my algorithm might be correct, maybe you were clever enough to think of a way that might be more efficient. And if you're clever like that, or you aspire to be, then I want you to head over to brilliant.org/dataskeptics to learn more about a site I try to visit at least a few times a week. In fact, this week alone, we're being featured on Brilliant.org's Problem of the Week. There's a fun combinatorics problem dealing with poker and probability. There's a link to that in the show notes and also from our site. It's not going to take you too long. It's a pretty straightforward problem, but you have to think about it for a minute. If you solve it, hit me up on our Data Skeptics Slack channel. I want to do something special for every listener that gives it a shot. It won't take you long, and while you're there, you can also check out the great courses and other fun activities at Brilliant.org. There's challenging new fun stuff going up on a regular basis. I've previously told you about how much I like their Artificial Neural Networks course, but also, if you just want to keep your mind stimulated, there's a great selection of a wide variety of these different puzzles and problems of the week that come up all the time. Join the community and exercise your brain a little bit. Head over to brilliant.org/dataskeptics and define specifically the problem of the week that's going on right now. Please help us out and see how many people we can get to give it a shot. That link will be in the show notes. And more generally, to see everything they've got to offer, check them out at brilliant.org/dataskeptics.
Now, do you think there are problems even harder than the shopping list comparison?
Of course.
Like what?
Let's see now. Getting dressed.
Well, okay, interesting. Let's go with this. Tell me why.
Because you can't wear 2 pairs of pants.
Right? So that should make it easier. You only have to select one item. So if you have n pairs of pants, n select one should be pretty easy.
You have to select 1 pair of pants, 1 shirt, and if it's cold, you have to add a sweater. Then if you're going to wear closed-toed shoes, you have to add socks.
Okay, so here's the procedure. Randomly select 1 pair of pants, 1 shirt, check the weather. If it's cold, wear a sweater. Add a random pair of socks, random pair of whatever else. That's like 6 steps.
No, but then also you have to account for what if you want to wear a dress? Dresses have the top and the bottom. What about a skirt?
I don't wear dresses or skirts.
Well, don't be sexist. This is for a woman. This ain't for a man.
All right.
I don't know why you jumped to that conclusion.
Well, it seems that you bring this up. I dress in constant time. That's my algorithm. I don't know what you're struggling with. Maybe I can help you.
I'm just saying you could wear a dress. You could wear a skirt. It's a wedding. I have been commented for not wearing a dress at a wedding.
Oh, yeah?
Yeah, people feel as a woman that they get a chance to comment on my attire, so they didn't think not wearing a dress was formal enough.
Well, that's an interesting topic for a more socially aware podcast.
So this is what I'm saying. This is a complicated problem.
Okay.
When to wear a dress, when to wear a skirt, when to wear shorts. You can't wear shorts at work.
If you want to convince me this is complicated, you're going to have to show me that the runtime is worse than n squared.
Well, I don't know. You tell me.
I don't think so. This seems like linear at best because you have n number of garments. You can parse them all to see if they're a fit for the situation. Of those that are a fit, you can randomly select one.
And then how does this algorithm decide when to wear a skirt, when to wear a dress, when to wear shorts?
So there would have to be some rules built in under the conditions under which you select those items. For example, if the event is a wedding, then don't select pants, only select skirts maybe. If the weather is cold, select a dress instead of a skirt. Those are constant time checks. Once you know the temperature, you can check that. Once you know the event, you can check it. And unless you have a very large number of those rules, you probably only have maybe 10 or 20 of them.
Oh, there's going to be more.
Why? What are all these rules?
Well, because you're going to the beach. Now you got to wear flip-flops. I mean, there's a bazillion rules. It goes on and on. Getting dressed is complicated.
But there can't be more rules than you have garments. That wouldn't make sense.
Oh, I think so.
No way.
Could be, right? You could have a uniform for work, uniform for school, uniform for this other job.
Right. If every garment you have is specialized to the task, then you have at most n number of rules because you have n garments.
Okay. So you could have equal to the number of garments.
Sure.
Probably, at least.
So again, the runtime for getting dressed is n.
But no, you could have more. You have multiple. Let's say you go to school. You have 5 pairs of school outfits. You have to decide which of them are dirty or clean to pick between the 5 of the school So then it's possible to have more than n.
Wait, why aren't the dirty clothes in the hamper?
We're messy people.
Okay, so how long does it take you to check if a garment is clean or not?
I mean, I just sniff it. I don't know.
Can it be done in constant time? That's one procedure. That's one step. You do one sniff for each garment.
Okay, you could do that. That sounds good.
So you discard those that don't pass the sniff test. So you have to do n number of sniff tests. And then of those that pass, you randomly select one.
Okay, that's
still a linear time algorithm.
Okay.
Let me help you out a little bit. If you wanted to say this was worse than linear time, one way to do it would be to say that your choice depends on someone else's choice. You and I don't necessarily coordinate, even though I'd be happy to if you wanted to. But if you said, I'm going to wear a blue shirt, and I said, well, I'm going to wear a green shirt, and you were like, green doesn't go with blue, so I'm going to switch to a red dress. And then I was like, well, if you switch, I'm going to switch. It's almost like we're playing a game now, where my choice is adversarial to your choice. That would end up very quickly being a lot like chess, right? Or a mini-max game. And those are exponential time, or worse.
Okay.
Or, here's another way we could do it. What if we claim that getting dressed is like the knapsack problem? The knapsack problem is figuring out, you have a bag with a finite volume, and you want to put certain things in it, but different things have different values to you, and you want to see what's the optimal number of things you can fit inside. So if your garments had to be coordinated, and the coordination was somewhat complicated, like certain things weren't good pairs, then it might be a worse than linear algorithm. That's another way. That would probably be a polynomial time. Yeah, something probably polynomial to do it like that.
I think that sounds more correct because, when we wear clothes, if something doesn't match color-wise or with my outfits, if I'm wearing tights, that usually means you want like a looser top. If you have a tighter top, you want a looser bottom. And there's proportions you're playing with. So, when you say it like that, there is an optimal fit for an outfit.
I'm glad we ended up in this example. This is a fun one. This is the basics of big O analysis. It's saying what's the worst case in the number of steps I would take, and you measure it based on the size of the input. And anything that we call polynomial time, that is, like n squared we discussed. You can also have n cubed, n to the fourth, whatever. Anything that has n to some number we consider to be efficient. We can probably solve that problem. When things are like exponential, like solving chess, we can't solve it exactly. Some problems are efficient, some are not, and there are even unsolvable problems. There's a world of really interesting topics here we're going to get into in the next couple of months, and we're going to relate them all specifically to topics data scientists will be interested in.
So what's an example of an unsolvable problem?
The halting problem.
The what?
The halting problem. This is like this is the cornerstone of computer science, actually. Alan Turing figured this out, that given a program, will this program ever halt on any input you give it? You're rolling your eyes at me. I don't think I got you on this one. Let's do
halt. What causes a program to halt?
It's programming. It's procedure.
Why would it halt, though?
Because it's done with its work. And it didn't fall into an infinite loop.
Does it need to fall in an infinite loop?
Well, we hope it doesn't. What good would a program be if it never completes running?
I don't know. That maybe that's when it freezes.
I shouldn't have said program, because when you think of a program, you think of like Chrome, and I never close Chrome, right? That runs forever on my computer. But an algorithm, some procedure I want to run, like I want to update the database, or I want to send out a t-shirt to someone who bought a Data Skeptic t-shirt, that should be a finite number of steps. So I want those things to run and be completed. So I know I didn't really get you on the halting problem there. We'll get into some of these other topics later. I think we're running a little long, but good episode. That's our intro to Big O runtime analysis, and we'll talk more about complexity topics in the future. Thanks as always for joining me, Lindy.
Thank you, Kyle.
And until next time, I want to remind everyone to keep thinking skeptically of and with data.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.